everybody. And we'll get started. I'm going to jump right into it. So, we're talking about dynamics of two-level systems. And when we're talking about dynamics, I'm talking about closed system dynamics. Then the dynamics is described in terms of the Hamiltonian and the Schrodinger equation, as we know. And so we have some Hamiltonian, and as we discussed last time, if we have a two-level system, then any operator that acts on the Hilbert space associated with a two-level system can be expanded in terms of some amount of the identity, some amount of sigma x, some amount of sigma y, and some amount of z. Every operator we can decompose that way. So there's some amount of the identity, I'll call that A0, and there's some amount of sigma x, sigma y, and sigma z, and we can kind of lump that all together in terms of a vector of coefficients ax, ay, and az. So every Hamiltonian has that form. I don't care what the two-level system is, it has that form. And we recognize this as the Hamiltonian that describes the physics of a magnetic dipole moment in a magnetic field. Okay? So this is equivalent to a magnetic dipole moment associated with spin in an external magnetic field. Which I'll call B. Okay? So why is that? Well, if I think about the magnetic dipole moment associated with a spin, then the magnetic dipole operator is proportional to the spin angular momentum. Okay? So S here is the spin angular momentum. And this proportionality constant is known as the gyromagnetic ratio. And the energy associated with the system, if I have an external magnetic field along some direction, is the same Hamiltonian or energy that we know from classical E&M, that the energy, the interaction energy, or in this case now the interaction energy Hamiltonian operator is equal to minus mu dot B. So that's what we know from classical, maybe we should know, from classical electrodynamics of when you put, that's the energy of interaction associated with the magnetic dipole moment in a magnetic field, okay? And so that will want to, we see that there's the lowest energy state when the magnetic dipole moment is aligned with the magnetic field, and the highest energy state is when they're So the dynamics, the quantum dynamics of a two-level system, also known as a qubit, is equivalent to the dynamics of a magnetic dipole moment in a magnetic field. And so I want to first talk about the classical problem, because everyone forgets and knows nothing about the classical problem. But the story is exactly the classical solution to what happens when you put a spin in a magnetic field. So I will digress for most of the lecture and talk about the classical problem, all right? So let's just think about this classically for a moment. So let's just imagine I have some spinning ball of charge, Q, that has some mass, okay? That spinning ball doesn't have to be a ball, it could be anything that has some orbital motion like this, has both a angular momentum, so that's its orbital angular momentum, and it has a magnetic dipole moment, because there are current loops, and those current loops give rise to a magnetic dipole moment. And the direction of the magnetic dipole moment depends on the sign of the charge. It could be along this, or depending on the sign. If this is a positive charge or a negative charge, then the magnetic dipole moment will be either along the direction of the angular momentum or anti-parallel. But when you do this problem, as some of you did with me last semester, you can find out what mu is, and it's equal to Q over 2 mass C L. Okay, this is in God's units, also known as CPS. Now playing the role of God. All right. Okay, so this is the gyromagnetic ratio, and very good. All right. So now we can ask also, what we know, there's also an energy. If I have a magnetic dipole moment in a field, it experiences a torque, okay? So the torque that is acted upon this vector, or on this angular momentum by the magnetic field, is mu cross B, okay? Or equivalently, gamma L cross B, where this is the gyromagnetic ratio, okay? For the cases that we're going to be interested in, let's say this is like an electron where Q is minus E, so this gyromagnetic ratio is negative, okay? It's a negative number if this is a negative charge. It'll make it easier for me to not have to keep track of many minus signs, as we will see in a moment. I could write this also as minus B crossed into L, and this I'm going to call, let's call this magnetic field for reasons later, I'll call it B naught, okay? So this is a particular magnetic field along a particular direction, B naught, and this I will call, this is a frequency. It has to have a frequency because this is equal, the torque is equal to the time rate of change of the angular momentum. Okay, mechanics. So there is this frequency here, which is what's called the Larmor precession frequency. Does it have the right units? Is this actually a frequency? Who would know? Well, let's just check. It's always good to check units. That's why we use CDS, because then we can check the units, because God knows what the units of mu naught and epsilon naught are. No one does. Some Faraday's order of magnitude is a Farad. Anyway, So let's just check. Omega naught here is equal to, in frequency units, the charge times the magnetic field divided by the mass times c. Does that have the units of a frequency? Well, yes, it does, because the charge times the field is a force. Like Q times E is a force, Q times V in CGS is a force, which is mass times acceleration. Divided by mass is acceleration. And so if I divide acceleration by speed, I get a rate. Voila! That's why we use these units. They're so much better. Because we can check our math, and we have to always check the units. You did that in freshman physics, you do it in 55th grade. You got to check the units. I'm in 55th grade. I decided. All right, so, all right, I'm digressing from my digression. So let's continue. So what is this equation of motion tell us? It tells us that the angular momentum of the spinning ball changes with time in this way. What is that? That's the equation of a gyroscope, right? Because it says that the direction, if this is omega, which is in the direction like that, and this is L, omega cross L is perpendicular to this plane, and that causes the thing to precess. That is Larmor precession. All right. Very good. And that's true, and since this is proportional to L, it says that also the mu precesses, because L is proportional to mu, the magnetic dipole moment will precess, okay? Whether the magnetic dipole is in the same direction as L or is negative, we're not gonna worry about that for the moment. Okay, so that's good, that's Larmor precession. The magnetic dipole moment, if it's not aligned with the direction of the magnetic field, right? This is proportional to the direction of the magnetic field, then it will precess. Now, I just said it wants to, the lowest energy state might be aligned with it, but unless I have any relaxation, any damping, it can't align. It wants to align, but it keeps getting pushed perpendicular, and thus it precesses around that. Yeah?
So the direction of omega naught is the axis it's precessing around, and then the magnitude is the frequency?
That's correct. Okay. The magnitude is, so omega naught is equal to the magnitude of gamma times p naught. Okay. That's what we had up there. Okay. Very good. So, all right. So now I want to talk about the idea of magnetic spin resonance. Which is at the heart of every MRI machine. It used to be called an NMR machine, but it's got the word nuclear in it, and that's scary. What is the idea of magnetic spin resonance? The idea of magnetic spin resonance is that I have a strong magnetic field along some direction, typically called the z direction, okay? If my spin, say, is, let's say, originally pointing somewhere down, and if I have a negative gyromagnetic ratio, so this is the direction of the magnetic dipole moment, that's actually the low energy state, right? If gamma is negative, if the gyromagnetic ratio is negative, then actually it wants to anti-align. This is the lower state. And this thing will precess around the B field at the Larmor frequency, omega naught, which is proportional, as we said, to B naught. Okay? And my goal now is to flip the spin. Okay? I want to, or in this case, it's not, I use the word spin. This is a classical magnetic dipole moment. I want to get this thing to flip the other side. Yeah.
I mean, it is spins. That one doesn't spin.
Yeah.
Is it right or left-handed precession around here?
It's right.
Okay.
Yeah.
What damping is stopping it from just aligning?
I'm just imagining there is no damping.
Oh.
If there is no damping, then it won't align. So we're looking at the closed system where there is no damping. Okay? Now, there can be forces that can cause it to damp, and then you're right. This is not the right description. But I'm in my spherical cow world with no udders or horns, and okay. So now the idea is I want to do the following. I want to flip the spin, and what I want, the way I'm going to try to do that is by putting on a magnetic field, an interaction field that's perpendicular to this, that it would cause it to precess around the perpendicular field. Okay? But this thing is rotating, so the torque that it's going to feel a little torque, and especially if this is a big rapid frequency, this transverse field is going to do basically nothing, right? It's going to cause it to wiggle a little bit, but it's not going to cause it to precess. So what we do is we rotate this magnetic field around in the XY plane, so we make this a time-dependent magnetic field. It has some amplitude that rotates around the z-axis with some frequency. Okay? Now, if the rotating field is rotating in the same direction as the precession, as I've drawn it in this right-hand way, and I choose my rotating field to be on resonance, so that the rate at which this transverse field, the angular frequency at which this transverse field is rotating, is the same as the natural precession frequency in V naught, well then I can go into the rotating frame that's co-rotating with this field. So in the rotating frame, my magnetic field is constant, right? And this thing is not precessing anymore. And so if I started it down here and I put this transverse field on, what's going to happen is that it's going to Larmor precess around the transverse field. And at what rate will it precess around the transverse field? Gamma times B transpose. I'll call that capital Omega. Yes?
Should it have a Z component?
No.
Then why does it have a Z component?
I'm saying
B transpose.
B.
No, yeah, you wrote E Z naught as one unit vector.
Oh, because I screwed up.
Oh,
I
sorry.
meant Y.
Okay.
Thank you. Thank you. So it's rotating in the XY plane, excuse me. It's rotating in the XY plane. And if this is the X, here's the X axis. If I'm in the rotating frame, I won't throw up. Then for me, it's always in the X direction. And this spin is, or magnetic dipole moment is not rising. And it will, now of course this whole thing is I mean, what's really happening in the lab frame is it's rotating like this at that frequency. But in the rotating frame, it's just processing around the x-axis and going from something close to the south pole to something north pole, and it processes at this frequency. Now, what if my so this is the frequency of the drive. I'm driving the system with this. And maybe before I say that, I want to emphasize an important point. The importance of resonance. This will happen no matter how tiny the magnitude of B perp is compared to B naught. If I didn't have resonance and if this wasn't off resonance, I'd have to crank up that field so hard in order to get it to go from the south pole to the north pole because I couldn't accumulate enough torque. But if I'm on resonance, the tiniest torque vector is going to accumulate the force. That's the importance of resonance, right? It doesn't matter how small the perturbation is compared to the natural forces. As if I'm on resonance, I can get a huge effect. Yeah.
So, talking about resonance, if
Yeah.
you crunch the appropriate math, do we get like a canonical resonance peak function that you see in electronics and stuff?
Yeah, well, again, there's no damping, so there's no
Okay,
line
right,
width.
yeah.
It's either you're on resonance or you're off resonance, right? It's, okay,
So it does bang.
yeah. We'll talk a little bit more about this. So now, what if I'm not on resonance? Okay? Now, if I was a good professor, I would have used the right blackboard so that I could put this one up so you can see. So, all right. So I'm going to draw the picture again. Oh, well. So here I am. It's that. Okay. So I got this B naught. I started this magnetic dipole like this. It's processing at this frequency omega naught, and I have this B perp, and this B perp is rotating, but it's rotating at a frequency omega naught. I mean omega. Okay. And suppose that the magnitude of this frequency is not equal to that. How would I do the mechanics of that? I want to go into the rotating frame, because when I go into the rotating frame, I have a constant torque, okay? So in the rotating frame, well, I'll call RF that radio frequency, the rotating frame. In that frame, the equation of motion is the true torque on the system, but I have to add a Coriolis force, a fictitious rotation, because I'm in a rotating frame, which is a non-inertial reference frame. God, whoever thought in quantum optics we would have to remember this, right? And what do I do? What's the fictitious? No. Thank God we don't have the prelims anymore.
Be related to circular motion or something?
Yeah, it's minus omega cross F. Okay. So I can think about this as like a pseudo-magnetic field. It's as if there was an additional magnetic field. This is known as Larmore's theorem. Larmore did all this stuff in E&M. Yeah. So this is because I have the fictitious, this is all in the rotating frame. Okay. So when I go into the rotating frame, I have to add this extra Coriolis force. Yeah.
Does that first term, do the units match up?
No, what the hell am I saying?
I-
Yeah, no, that makes no sense. And thank you, everyone. Yeah, you know, God, it can be wrong. No, yeah,
Okay.
yeah, thank you. But what I did mean to say, because I was thinking ahead, is that this torque is equal to, well, I have omega naught, that's the precession due to B naught, plus the B per omega cross L. So this is what I had. This is coming from gamma B naught, and this is gamma B per. Those are the two fields that are causing the angular momentum to torque in the rotating frame, okay? But in addition to that, I have to add this term. And so the equation of motion I get of what the angular momentum does in this frame is I get something we call minus delta cross L plus omega cross L, where delta is the frequency of the drive minus the resonance frequency. Okay, that's my definition. And this is the magnitude of delta is known as the detuning. It's how far I am off resonance. Okay, the sine of delta. So in this case, this is in the z direction. Omega delta is equal to omega minus omega naught in the z direction. Because I put my magnetic field in the z direction, and the direction of the angular velocity vector of the rotating magnetic field is also in the z direction. Everyone see that? It's rotating like this, so this vector is pointing in the z direction. Okay? So this is delta. That's the detuning, and when delta is less than 0, we call it red detuning, because it's to the red of the resonance. And when it's greater than 0, we call it blue detuning, because it's got a bluer frequency than the resonance frequency. This is the sign convention that we'll always use. The drive frequency minus the resonance frequency, okay? Oh, there's something already written on there. God, who is doing that? All right, so, all right, with that said, what is thus the precession of the angular momentum, or the spin, or the magnetic dipole moment in this case? Well, it's pretty simple. Here it is. This is all in the rotating frame. What this is equal to is omega effective crossed into L, where omega effective is omega minus delta. Everyone see that? Okay. So the equation of motion of the angular momentum vector is the equation of a gyroscope, with this as the precession frequency, which has a magnitude omega squared plus delta squared square root, and a direction that has an x component and a z component. Okay, so here's a sphere. We have some amount of, let's say we have, in this case, blue detuning, so that delta is a positive number, but it's a minus delta over there. So I have, this is omega, this is delta, and this is the vector omega effective. Okay? And so if I start the spin somewhere like this, what it's going to do is Larmor process with the right hand rule around omega effective, and at what angular speed will it process around this axis? It will process at this rate, the magnitude of omega effective. So it's going to process at a rate, at an angular speed, omega effective, which is the square root of omega squared plus delta squared. In contrast to when I was on resonance, where I rotated at omega, when I'm off resonance, I rotate at this faster speed. Moreover, it never gets as high on the North Pole as it was on the South Pole. It will never get all the way. If I started at the South Pole, it can't get to the North Pole. The deficit depends on the detuning. Okay. Nate had a question first.
Because omega effective is omega minus delta.
It's the vector is this. It's got a component which is it's got a component along the x-axis and a component along the z-axis.
So is that the vector delta or just a vector with magnitude delta?
This is the magnitude of this vector. This is the magnitude of that vector. So it's got an x component and a z component. And the length of this vector, go Pythagoras. Okay? Yes, Ben.
So the on resonance omega is actually a minimum precession speed, whereas
Yep.
yeah, so not a maximum. For to get off resonance is when you
Off resonance, it goes faster.
It goes faster around, but it won't get as
Well, I don't know which are. So this is in the rotating frame. Remember, I'm going to make the noise again. This thing is all processing in the lab frame at the precession frequency omega naught. That could be a huge frequency. These are generally slower because typically I put this in a huge, maybe you've never had an MRI because I haven't had one myself, but there's like Tesla, all right, that's SI units, thousands of Gauss of magnetic field, and then there's a tiny RF rotating field. So these frequencies are generally small compared to omega naught. And they're also small, so there are 4 different frequencies. Omega naught is the natural precession frequency in the static field. Omega is the frequency at which I'm rotating this field, and the difference between them is delta, okay? And which is typically small because I want to be close to resonance. And the 4th frequency is the Larmor precession frequency, capital omega, which is the frequency at which I would process if I was on resonance. Yes?
Since you're looking at the magnitude of the vector, are you only going to take the positive root there, or are you going to?
Yes, because that's the frequency, it's the frequency at which it processes. Okay, ta-da, we solved the whole problem.
no quantum mechanics.
Really? Okay. So now I want to say, what is the quantum mechanical description of this? Let's go back to the Hamiltonian. Okay. There it is. So this was in the rotating frame. Okay. So now we're going to do the quantum mechanical description of the same physics with the same Hamiltonian. Now, I'm going to first start so what I said is that this was equal to minus mu dot b, where mu is now an operator related to the spin angular momentum operator. Okay? Which I can write as omega naught dotted into S, where omega naught is minus gamma b. Omega is going to be less than 0. Okay? I mean, gamma. I'm not taking out the h bar, so this says units of h bar omega is an energy. Okay? So I'm going to solve this first in the Heisenberg picture. Because the Heisenberg picture has the most natural connection to the classical components of the angular momentum, okay? So I want to look at some component of angular momentum. I want to know how it changes as a function of time according to Heisenberg's equation of motion. How would I do that? Minus I over h bar, the commutator of SI with the Hamiltonian. Okay? So that's Heisenberg's equation of motion for that component of spin angular momentum. The Hamiltonian itself is this, which is the sum over components. I'll just write it just generally. I'm not going to say it's in the z direction. I'm just sub j, s sub j. I'm using a different index because i's already taken. Never reuse the dummy index. This is the dummy, duh. Don't reuse it, all right? So this is then equal to minus I, another I, sum over j, omega sub j, the commutator of s sub I with s sub j. Everyone with me? And what is this commutator? It's the angle, everyone knows it, I hear it. It's this minus the square root of 1, also another I, epsilon ijk, sk sum over k. There's an h bar in there as well, okay? So this tells me that this is equal to the i's cancel, the j's got kept, a sum over j and k, epsilon I j k, right? And this is the ith component of that by the rules of cross products. And so we find the Heisenberg equation of motion, ta-da, is exactly the same as the classical equation of angular momentum that we had for orbital angular momentum, but now for spin, it doesn't really matter. It's equal to omega cross s. Okay? Which means that if I were to ask about, for any state of the system, the expected value of that operator, which is the mean spin vector, undergoes the same Larmor precession. Exactly the same Larmor precession as the classical spin does. It's not always the case that that's true. There are very few kinds of equations of motion by which the classical mean value moves along the quantum mean value moves along the classical trajectory. The harmonic oscillator is one such example. The other is Larmor precession. Okay? So, very good. So now I want to think about spin magnetic resonance from the point of view of quantum description of spin magnetic. I'm going to do the same experiment in my idealized world with no damping, I prepared the spin in some state, and I'm going to put on these fields, and I want to flip the spin, okay? So I need to find the equation of motion, I need to find the equivalent of going to the rotating frame, okay? The Hamiltonian in spin magnetic resonance is this one. So I have the magnetic dipole operator, vector operator, and I'm putting it in the magnetic field, which is a combination of the static field along the z direction. And then a transverse field, which has some magnitude b perp. And I want to find the equation of motion of the spin operator. Now this is a time-dependent Hamiltonian. And that's generally nasty to deal with. But I can make this Hamiltonian time-independent by going into the rotating frame that's co-rotating around the z-axis. The frame rotates at frequency of the drive, okay? Not the natural resonance frequency, it's not quite the same as the interaction picture, because that's usually you're talking about the H naught part. I'll come back to that, the slight difference between the interaction picture and the rotating frame. So, in quantum mechanics, if you want to go into a different reference frame, do that. How do we do a frame? Yes, Dave.
Change of basis?
A change of basis, and that change of basis is obtained through a rotation operator. So I'm going to digress now to talk, we haven't talked about, so let me just say, so the going to a change of frame means a unitary transformation. That achieves the change of basis. Now, in this case, that change of basis is a rotation. We want to go to the rotating frame, okay? So the frame we're going to is, we want to go to the rotating frame. Which is rotating around the z-axis with angular frequency omega, frequency of the drive, okay? So how do we achieve that? We achieve that with a unitary transformation, which is a rotation operator. That rotation operator is an operator that acts on Hilbert space. Again, we have to remember we're talking about two vector spaces and spaces in general. There's Hilbert space, which defines the state of the quantum system and upon which operators act, and the three-dimensional space. But the physical operators that we talk about connect the lab to Hilbert space, okay? So I want to talk about the rotation operator. The term rotation has different meanings. There's a rotation in Hilbert space, and there's a rotation of a vector in three-dimensional space. what I mean by a rotation operator is something that rotates a vector in three-dimensional space. But it's an operator that acts on Hilbert space. So what is the rotation operator in quantum mechanics? It's generated by angular momentum. That's what connects the world. What's really true about observables is about the symmetries of the universe, not about measurement. They're not about Hermitian. It's the things that are the generators of the symmetries of the world. And rotation is one of those symmetries. Whether we're talking about rotations as described by classical mechanical description or quantum, it's the same symmetry. And the generator of rotation is angular momentum. So the rotation operator, which I'll call D, because other people also call it D, is defined as follows, circle H range, is e to the minus I theta n dot L, if it's orbital angular momentum, or generally I'll call it J, where J can be L, S, or combination. Okay, so if J is an angular momentum, and an angular momentum in quantum mechanics we include both orbital and spin, then this is divided by h bar is the rotation operator. And what it does is the following. If I look at the unitary transformation on a vector, so I have a vector operator, like the position vector, or the magnetic dipole vector, this is a vector operator, then I look at the unitary transformation on the different components, then what it does is it rotates the vector. I love this. This is as cool as it gets. Well, maybe not as cool as it gets, but it's pretty damn cool. I want to unpack this and then try to understand what this is saying. So on the left-hand side over here, I have a unitary transformation on an operator, okay? Which is equivalent, as Nate says, to a kind of change of basis. There are three components. This could be, say, X, Y, and Z, the X, Y, and Z components of position, or it could be PX, PY, PZ, the three components of momentum, or it could be LX, LY, LZ, it could be the three components of orbital, it could be SX, SY, SZ, the three components of spin. It's a vector operator. And when I do this unitary transformation, what it does is the operator on the left is just a rotated version of the vector operator with this is an SO3 rotation matrix. That is the thing, it's the thing that in classical mechanics you've learned, it's a rotation matrix. Okay? I know. Omar is pretty amazing. Yeah. So that's what we mean by a rotation operator. It's a thing that rotates a vector. This is in three-dimensional space. The sums here are over X, Y, and Z, whereas this is something in Hilbert space. Okay.
What is the name of this theory?
It doesn't have, it's just the way it is.
I can't remember.
Yeah.
So on the left-hand side is our operator in Hilbert space?
Yes. This is an operator in Hilbert space. This is also an operator in Hilbert space. But
the matrix is
the matrix is summed over the different, whether it's the X, Y, and Z components.
Oh, I see.
Yeah.
So our V is an operator that acts on Hilbert space, but it transforms like a Cartesian vector.
That's correct. It transforms like a Cartesian vector. That's exactly right. That's what. If I have three matrices that put together do this, then those three matrices form the components of a vector operator. This is the definition of a vector operator. If you have three operators which rotate each other this way, then that is what we call a vector operator. Examples of vector operators. The position operator is a vector operator. The momentum operator is a vector operator. The angular momentum is also a vector operator. The spin vector operator is also a vector operator under X,
Not under.
L. Yeah, because it wouldn't rotate under L. It commutes with L. Yes,
Isn't that only a sum over J?
yes, that's correct. Thank you. Yeah. Yes, thank you. Yes, Bob.
And vector operators you can also write as spherical tensors. Right?
Oh yeah, that we could go down the Victor Eckhart. I could talk about that forever, but you know we don't have forever. All right, I want to continue. Now, let's now do the following. So now I want to look at the Heisenberg equations of motion in the rotating frame. Okay. So my spin vector in the rotating frame is going to be equal to, in this case, I'm going to rotate around the z-axis by an angle that is omega t. Okay? So d sub z is the rotation operator that is rotating me around the z-axis at this frequency. So the amount, the rotation angle is omega t. Okay? So this is what we just said, to transform to the rotating frame, I need to do a unitary transformation where the unitary is the rotation operator associated with going that frame. Okay? Everyone clear on why this is omega t? That's the angle at which I rotate. So now I want to find the equations of motion of this operator in the rotating frame. In the same way that we looked at the equation of motion of the orbital angular momentum in the rotating frame. And we just did it without going through all the details. I just said, you all remember classical mechanics, and you have to add the Coriolis force to that. You'll see. Well, I can just do it. So now let's look at the time rate of change of this operator in the rotating frame. Well, that's going to be, and I'm going to just, I'll just simplify, just call it D. I'm not going to put all the do's and dads on it. And this is going to be equal to this plus, this. Oh Lord, they're hats, not vectors. Plus this. Yeah.
Should the omega in the rotation operator be a vector? Yeah, the dot vector in that
Are you missing a E?
That should be a vector. Or I could frequently, let me write it more simply, excuse me. I'll just call it SC. Right? Yeah. Okay, so this is, I just wrote it out. Let's do it. This we already had. This is the Hamiltonian in the lab frame. This is minus I over H bar S times H of T. That's the Heisenberg equation of motion in the lab frame. In the lab frame, this is the Hamiltonian. It's up there. Okay? Now we have to do these pieces. Let me just say that this all together, if I put it all inside the commutator, this is equivalent. I will leave that as an exercise to the reader. You are the reader. Okay. So that term is the commutator between the spin in the rotating frame and the unitarily transformed Hamiltonian. Okay? But then there's more. Okay? In fact, this Hamiltonian, when I go into the rotating frame, is going to be equal to minus mu dot B0 plus B per in the x direction. So when I go into the rotating frame, the Hamiltonian is time independent. In the rotating frame, I'm rotating with that, and the Hamiltonian, just like in quadratic mechanics, when I were to do all that out, I find this. But that's not, but what about this stuff? This stuff is this. It's the part that effectively gives me Larmore's theorem.
Coriolis.
It's the Coriolis-like thingamaboozin. So let's just do it. If I take the time derivative of that dagger, I get plus I omega S Z over H bar times D dagger S D. That's the first term over here. Okay. And then I have plus D dagger over here, I have that is equal to D times minus I over H bar omega SZ. SZ and D commute, so I can put them on in any order I like. And this is equal to S in the rotating frame. Okay. So, interesting. What is this term? Well, what this term is equal to, it's equal to minus I over H bar, the commutator of SZ with minus I over H bar, this, yep. Okay. So, which I can think about as omega dot S if I wanted to. Interesting. Once again, so now let's put this all together. What I have is that it looks like the following. It's again a Heisenberg equation of motion, but with a new Hamiltonian. And the new Hamiltonian is the unitarily transformed old Hamiltonian. And then there's a term which is minus omega SD.
Oh, you wrote it backward then.
No, I didn't write it backwards. Did I? Where did I? Oh, signs, joys upon joys of the signs of this thing. out that I got this right. I know that this is correct. The question is, where did I go wrong?
The second commutator you did, since you built up the negative I over h bar, if you just switch the order of your commutator, it should work.
Oh, yes, that's right. Okay, so yes, because this is S. Okay, so this is S omega SZ with a minus sign. Yeah, thank you, Dixie, that's correct. Good, all right. Phew, commutators, minus signs. I spent half my life looking for minus signs and the other half looking for factors of 2. It's what else is left? All right, so notice what we have here. We have exactly now if I call this omega dot S, then this equation of motion is just like we had before. This is equal to the equation of motion for the spin is exactly the effect of the Coriolis force that we had before. There's something minus omega cross S, which is exactly what we had over here. So going to the rotating frame gives us this exact force, which is like, in this case, a pseudomagnetic field. If I wanted to think about this as a magnetic field, I would subtract mu dot B, where B is minus gamma omega. I have a additional fictitious magnetic field going to a rotating frame with a charged particle is like a fictitious magnetic field. So I'm gonna do this now. I'm sitting on the merry-go-round, and I throw a baseball. The baseball will curve. Now, I'm very bad at throwing a baseball. I'm really bad. It's one of the telltale signs. I really can't throw a baseball. But if I could, it would curve. And if it's a charged particle, that looks like there's a magnetic field that it charged. So a force on a charged particle in a rotating field is like a fictitious magnetic field. Okay. So with all of that said, what we have with this put together, with this Hamiltonian, as was just written somewhere, where did it go? Where did my Hamiltonian go? Oh, it's over there. Is equal to minus omega plus omega naught SZ yes, that's correct. Plus omega S. And the equation of motion we have is exactly what we had before. This is the detuning. So, what we have learned is that the Heisenberg equation of motion for the spin vector, given this resonance picture, is exactly the same as the classical equation of motion. And so with that said, what we have is that the spin vector, if I look at the expected value of the spin vector, it processes exactly as the classical angular momentum processes. It processes around the direction of this vector with a speed, an angular speed, which is this. And that's it. This is in the rotating frame. I won't make the noise again. So here's the sphere. If I start the spin here, and I have some detuning, I get the spin, the mean spin, processing around this vector, which has these components at that speed. Now, let's specialize the case of spin 1/2. For the case of spin 1/2, we know that the spin angular momentum vector is h bar over 2 times the vector of Paul's, right? And so if I have some state, let's say a pure state, doesn't really matter, then we know that the block vector is this. The block vector defines the state. It defines the state of the system. We say any state of the system can be expressed, let's not even say it's pure, it doesn't even matter, that way. So if I know what Q is, I know what the state is, right? So what happens to the block vector as a function of time? Well, this equation tells us in the rotating frame, because I now can write both things in the rotating frame, which means the block vector just processes. And it processes around the direction of omega effective with that frequency. Right? Because I can just plug in for S here, h bar over 2, the h bars over 2 cancel, and the block vector undergoes logarithm precession. The block vector undergoes logarithm precession. The block vector is what Bloch talked about when he's talking about the direction of a spin. But what's amazing here is this was true no matter what two-level system we were talking about. It didn't have to be a spin at all. It could be any old qubit as long as we call one of the states spin down and the other state spin up. This is no longer the direction, if I think about this as Q, the direction of the block vector, say it's a pure state. This could be two levels of an atom. It could be the horizontal and vertical polarizations of a photon. It could be the two modes, as we'll talk about a dual rail qubit for an interferometer. This is in some sense an abstraction. The block vector doesn't necessarily represent a direction in physical space. It's a pseudo spin. Emphasis on pseudo, meaning it's an imaginary spin where this is the one direction, this is the two direction, the three direction. They're not the directions of anything in physical space. But we've solved for how the state evolves as a function of time, in this case, using the Heisenberg picture, and then taking the expectation value to get the block vector. And once we have that, we see that the block vector will just larm or precess in the same way that my classical mechanical ball of spin does it. God, isn't that awesome? Okay? Yes?
Are there any differences between the angles?
Nothing.
Processes?
Nothing. It's exactly the same. This is just a proportionality constant. Yeah?
I know that the block vector is somewhat dependent upon the polarization of the states. So if the block vector is processing, what does that mean for the polarization of my state?
It's changing.
It's changing over time.
Right? So if I have something which is, polarized in some direction, as a function of time, its polarization is changing. Now, the purity doesn't change in this. There's no damping. So, it's just processing. If it starts on some radius of the sphere that, if it's a mixed state, it also processes in exactly the same way, but on the inner sphere. If it starts with a certain amount of purity, well, that purity is preserved. Yes?
That equation tells us about the physical components of speed, Sx, Sy, and Sc.
That's correct.
And that one tells us about the block vector.
But they're the same thing, so let me again, maybe I'll take this board over here.
Sorry, you erased it. Is that S a rotating frame, those S's?
Everything's in the rotating frame here, yes. Thank you. Thank you, Eric. Yeah. Now I'll erase it. So, let me try to address your question in the following way. Let's say, as we will talk about probably next lecture, we have a two-level atom. Okay? And I have two states. I'll call one the excited state and one the ground state. And I'm just going to say this is a qubit. Okay? So this becomes my spin down, and this becomes my spin up. I can call either one or the other up or down, but along the z-axis. Now this z-axis is an imagined z-axis. This has nothing to do with the physical direction of anything. Okay? So calling this a z-axis is a little confusing because there ain't no z-axis. There's no magnetic field. There's nothing. This is just, I just treat it as if it were that. Okay? In which case, my Pauli Z, which we would sometimes call Pauli 3 to ensure that we don't confuse ourselves with X, Y, or Z, is what in terms of these states? Nate, yes?
E minus ground state, ground state.
Thank you. So that is my Pauli Z operator. My Pauli X operator is what? In terms of E and G. Right? This is sometimes sigma 1, sigma plus sigma minus. Sigma plus in this case is related to absorption going from the ground state to the excited state, and sigma minus is like emission going from the excited state to the ground state. And sigma 2, also known as sigma y, would be Eg minus Ge over I. Okay? So this is I just want to conclude with this important relation. We're going to come back to this. I haven't talked about it. let's think about the components of the block vector. So what are the components of the block vector? The components of the block vector in this case is the expectation value of the powers. Okay? Now, Bloch himself called those three components the x component u, the y component v, and the z component w. And sometimes we do that. So these are the three components. So u is the expected value of sigma x or sigma y. I'm going to call them x, y, and z, because. But again, I want to emphasize this has nothing to do with any physical direction. It's just the algebra of the Paulis. So let's look at this guy. And this is then equal to the trace of the density operator with sigma x. This is the trace of the density operator with sigma y. This is the trace of the density operator with sigma z. Right? And let's plug that in over here. What I see is that this is equal to, if I take this and use the rule, I get rho GE plus rho EG. Everyone see that? Which is twice the real part of that off-diagonal element. This is rho GE minus rho EG over I, which is twice the imaginary part of rho, let's call it GE. And this is equal to rho EE minus rho GG. The point I'm wanting to emphasize here is that the three components of the block vector, which we represent as points on in a three-dimensional space inside this ball, if it was a true physical spin, would correspond to the components of that spin. But if it's a pseudo spin, then those three components represent something about coherences and populations. They're pseudo spins. They're not actual spins, but they satisfy the same algebra, the same as a physical spin that was pointing in a physical direction. These directions have nothing to do with the directions in space that define the atom. So these things have to do with coherences. And this thing has to do with what we call population. That is to say, the probability to be in the excited state compared to the ground state. And so but what we learned and what's important and why I went through this, because you learn these things, but you don't remember. No one ever teaches you that this is just a gyroscope. I mean, come on, you're a physicist. You need to know what a gyroscope is. It's not just zeros and ones and qubits. We're still learning physics. Okay. All right. Very good. We'll call it quits for now.